Hi, welcome to class. My name is Professor Don, and this week in our class, we are learning Module 5 numbering systems. If you are watching this class live with me now, wait till the end of the presentation to ask your questions. If you are watching it online in our NetAcad classroom, ask your questions in the help discussion forum, or if you're watching it on YouTube, ask your questions in the comments below, and I'll be happy to answer those questions for you. Let me go ahead and share my screen. And do a couple adjustments, open the chat room in case I ask for help. Start the presentation. And one second. All right, we're there. Module 5, numbering systems. So we're going to calculate numbers between decimal, binary, and hexadecimal. And that's what it says below. Binary numbering system. The binary and IPv4 addresses. Why do we need to know about binary and how the computer talks to how the computer processes information? Well, binary numbering system consists of ones and zeros. It's all the computer knows. Decimal numbering system consists of digits 0 through 9. So in the binary world, a computer is communicating in ones and zeros. The network address, 32 bits, and then the 24 stands for another 32 bits, which is a subnet mask. So a computer only understands ones and zeros. So this is what the network address is. This is the IP address for this computer. This is the IP address for, this is the IP address for this port. This is the IP address for that, but you get the idea, right? So it only understands ones and zeros. We understand decimal, so we understand 0 through 9, and then we carry. So we can set an IP address of 192.168.10.10, and that is a whole lot easier to remember than 11000000. You get the idea, right? So this is how we talk about the way a computer is connected, for example, and how we actually assign addressing for ports, for example. So host servers and network equipment using binary addressing use binary addresses to identify each other. Each address is made up of a string of 32 bits divided into 4 sections called octets. Each octet contains 8 bits. 8 bits is 1 byte, very important number of bits, 1 byte, separated by a dot. For ease, we use dotted notation instead of, it's called dotted decimal instead of just typing in the zeros and the ones. I'm going to show you a video. It's going to review decimal, so you can compare decimal to binary, and then it will convert an IP address, or maybe just a P address. No, there's a typo there. An IP address in binary to a decimal numbering, So let's watch this video.
In this video, I'm going to discuss binary to decimal conversion. But before I do this,
by the way, these videos, before I started, these videos are also in our NetAcad classroom. And if you go to IT Answers, I always forget the name of that address. What is that address? Let me get it for you. In case you have a poor connection to the video, you may want to see it online. And you can see these videos at itexamanswers.net. They don't pay me to tell you that, but that is a place. It's itanswers.net. They have the same videos that I'm showing here, and it's out on the web. All right, here we go.
going to discuss binary to decimal conversion. But before I do this, I want to take a look at positional notation or place values. I have the number 2,168 here. If we look at the place values of the number 2,168, we can see that the place values have the ones place, the tens place, the hundreds place, the thousands place, 10,000, 100,000, and million. These are the place values of the base 10 decimal number system. You can see that we have the number 2 in the 1,000s place, so we have 2 1,000s. We have a 1 in the hundreds place for 100. We have 6 in the tens place for 60, and we have 8 in the ones place for 8. So effectively, we have 2 1,000s, 1 100, 6 tens for 60, and 8 ones for 8. Now, when we're talking about the place values in the decimal number system, we're talking about the powers of 10. You can see that the ones place is the 10 to the 0, the tens place 10 to the 1, the hundreds place 10 to the 2, or 10 times 10, which is 100. The thousands place is the 10 to the 3, or 10 times 10 times 10, and so on and so forth. So you can see that the place values are based on powers of 10. If we look at the number 2,168 then, in long form, we can see that effectively we have 2 1,000s, 1 100, 6 tens, and 8 ones, and 2,000 plus 100 plus 60 plus 8 totals 2,168. This is the type of counting and addition that we learn as children. The decimal system is base 10. It's based on the fact that you have powers of 10, but more importantly, you have 10 characters or 10 numerals in this counting system, from 0 all the way up to 9. So that means that in each place value, you can have anywhere from the number 0 up to the number 9. In other words, if I had the number 9,168, I'd simply replace the 2 here with a 9, and now I have 9 1,000s totaling 9,000 in the 1,000s place. So in any one of these place values, you can have the number 0 all the way up to 9. This is the base 10 decimal number system. If we consider binary and look at it in the same light as decimal, binary is a base 2 number system. There's only 2 characters or 2 numbers, 0 and 1. So under the place values, we can only have zeros or ones. The place values go from 1, which is 2 to the 0, to 2, 2 to the 1, 4, 2 to the 2, 8, 2 to the 3, or 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 is 16. That's 2 to the 4th power, place value of 16. The 32's place, the 64's place, and the 128's place. Notice that I extended the table to 8 place values. That's because 8 bits is an important grouping of numbers. 8 bits makes a byte in computer processing. So now I have the place values for essentially 8 bits. If I want to write the number 168 in binary, I just have to find the corresponding place values and plug in either a 1 or a 0. So I'll go to the 128's place and ask myself, do I need 128 to reach 168? Yes, I do. So I'll put a 1 there. Now, do I need a 64? I already have a 128. If I add 64, I would get 192 because 128 plus 64 is 192. So the answer is no, so I put a 0. I still have 128 now. Now, do I need a 32? 128 plus 32 is 160. So yes, I could use a 1 here. Now I have 160. Do I need a 16? No, that would make 176, which would go over my target number of 168. I'll put a 0 here. What about an 8? If I add an 8, I'll hit the number perfectly. 128 plus 32 plus 8 is 168. I'll follow this up with zeros in the 4's place, the 2's place, and the 1's place. And 168 in binary equals 101010000. I now have one 128, I have one 32, and I have one 8. And 128 plus 32 plus 8 equals 168. If we go to the next slide, you can see now that I'm now charged with converting the number 0110101 to decimal. If I want to go the opposite way and convert this binary number to decimal, all I need to do is plug it into the place values. I'll put it in here, 0, 1, 1, 0, 1, 1, 0, 1, and then add it up. I have a 64 and I have a 32. 64 plus 32 is 96. Plus I have an 8, that makes 104. Plus 4 makes 108. Plus 1 makes 109. This number converted to decimal is the number 109. Now let's look at a full IP address in binary. I'll go to my next slide. And you can see in this next slide, I now have a 32-bit IP address, 4 octets, or 32 bits total. If I want to convert this binary IP address to decimal, all I need to do is count up each individual octet. Let's start with the first one right here. We can see that 1, 1, 0, 0, 0, 0, 0, 0. 128 plus 64 is 192. Now, the next octet has 10101. Let's do that one. 0, 1, 0, 1, and then all zeros. If we count up the numbers, 128 plus 32 is 160, plus 8 is 168. The next octet is all zeros with a 1 in the last place in the ones place. This is easy. This is the number 1. All zeros and a 1 in the ones place makes the number 1. And then finally, we have a number here. I'll plug it in here to my table. And I have the number 011000101. We can see that 64 plus 32, we've already said, is 96. Plus 4 is 100. Plus 1 is 101. So the conversion of this binary IP address to decimal is 192.168.1.101.
All right, I see here in my chat room that students are saying IT exam, the IT examanswers.net isn't working, and but I'm sure that video is out there in another place. It's just where I was going. Hopefully my recording isn't too bad. Hopefully they're just down for a short period of time. That or Cisco found out they had the videos out there because I was talking about it and they brought it down. One or the other, I don't know. We'll find out. Well, maybe we'll never find out. So these next few slides just reiterate what he said about how we every day convert in decimal. Say for here in the United States, we convert dollars using decimal. So if you have $192, that's 109 tens and 1 1. And then it shows you how binary notation is the exact same thing, except we're just not as familiar with it. But you basically do the exact same thing. And we always work with a group of 8 bits when we're dealing with binary, at least when we're talking about computers, because we work with bytes, and in dotted decimal, IPv4, there's 4 sets of 8 bits to get to 32 bits. And then they just show it to you here, converting our binary number up here at the top, and they just convert it like they did in the video. Here's the binary number, the whole thing, and then they just break it down for each one of the octets. And they also talk about how to get there, converting decimal to binary. Basically, are there any, if we had a number, let's say it's 168, are there 128s? If there are, you put a 1 in there. If there's not, you don't. Then you subtract that number, 128 from 160, whatever I just said, leaving you so many, and then you go down the line from that point. And then they give you an example here with the number 168. We saw that in the video. And then they show you breaking down the fact that a router only sees ones and zeros, but we write and we see dotted decimal. And be thankful. Hexadecimal numbering system. Well, IPv6 uses hexadecimal, so we have to understand IPv6 addresses. You must also be able to convert hexadecimal to decimal and vice versa. Hexadecimal is a base 16 numbering system that uses the digits 0 through 9, just like we do in decimal, and then they add in A through F. So A is 10, B is 11, C is 12, etc. F is 15. It is easier to express a value as a single hexadecimal digit than as 4 binary bits. Hexadecimal is used to represent IPv6 addresses and MAC addresses. And here they show you what decimal would look like, 0 through 15. This is the binary equivalent. Notice 15 is all ones. And then in hexadecimal, it's 0 through F, and F is 0, all ones, or the number 15 in decimal. Now, IPv6 addresses are 128 bits in length. Every 4 bits is represented by a single hexadecimal digit. That makes the IPv6 address a total of 32 hexadecimal values. And you can see them here. The figure shows the preferred method of writing out IPv6 addresses, with each X representing the 4 hexadecimal values. Now, those hexadecimal values, this X can be anywhere from 0000 to 0001, 002, 00F, 0010, on and on, all the way up to FFFF. Now, each 4 hexadecimal character group is referred to as a hextet. And then each one of those letters represents a group of 4 binary numbers. So the first F can be anywhere from all zeros to 11111. And as we learned in the previous screen, 1F is equal to 1111. So then you need the second F and the third F and the fourth F. Don't worry if this is a confusing slide. I think I taught Cisco 2 or 3 years. Nah, just kidding. I understood it immediately. All right. So it took me a little while to understand this slide. I understood the concepts, but the way they broke it out was a little challenging. I have a video here that's going to talk about the characteristics of the hexadecimal system. Then it will convert from hexadecimal to decimal, and then convert from decimal to hexadecimal. So let's get that video started.
Hexadecimal, or hex for short, is a base 16 number system. It uses 16 symbols, the numbers 0 to 9, as well as the letters A to F. It is based on powers of 16. If we follow the same procedure used for converting binary to decimal, we can write out the place values or positional notation for the hexadecimal number system as well. Here we can see the first 4 place values based on powers of 16. This is 16 to the power of 0 or 1. Any number to the power of 0 is 1. This is 16 to the power of 1, or 16. This is 16 to the power of 2, or 16 times 16, which equals 256. and this is 16 to the power of 3, or 16 times 16 times 16, which equals 4,096. Let's look at the decimal and binary equivalents of each hex symbol. These are the decimal equivalents. Note that the hex symbol A is equal to decimal 10, hex B is equal to decimal 11, and so on until we get to hex F, which is equal to decimal 15. Here are the binary equivalents. Note that each hex symbol can be used to represent a 4-bit binary number. Given that 8 bits is a common binary grouping, we can represent an 8-bit binary number using just 2 hex symbols. In this first example, let's look at converting hex 2A to decimal. First, I'll write out the positional notation for the first 2 powers of 16, then insert the hex symbols below the corresponding place values, 2 under 16 and A under 1. Then I'll multiply each hex symbol by the place value that it's under and add the results together. So we get 2 times 16 plus A times 1. That gives us 2 times 16 plus 10, which is the decimal equivalent of A in hex, times 1, which gives us 32 plus 10, or 42 in decimal. Multiplying or dividing by 16 isn't always easy when doing hex to decimal conversions. Usually it's easier to convert the hexadecimal or decimal value to binary first, then convert the binary number to decimal or hexadecimal. Let's convert decimal 197 to hex. First, I'll begin by converting 197 to an 8-bit binary number. Here I've drawn out the first 8 place values of the binary number system. We need to find out what combination of these place values adds up to 197. I'll begin by writing 197 on the left side, and starting at the left, if the place value is equal to or less than this number, I'll put a 1 under it and subtract it, and if it's greater, I'll put a 0 under it and move to the next place value. Since I can subtract 128 from 197, I'll put a 1 under it and subtract it, and that gives me 69. I can subtract 64 from 69, so I'll place a 1 under that and subtract it. That gives me 5. 32 is too big, so I'll place a 0 under that. 16 is also too big, so that gets a 0. 8 is also too big. But when I get to 4, I can subtract that, so I put a 1 there, and I subtract it here. 2 is too much, so a 0 goes there, and 1 is just right, so I subtract it, and it results in a 0. Therefore, decimal 197 equals binary 110000101. Next, I'll convert the 8-bit binary number to decimal by first splitting it into 2 4-bit binary numbers, and then I'll rewrite the first 4 binary place values above each half. So here I have 1, 2, 4, 8, and then repeated on the left, 1, 2, 4, 8. Then I'll convert each half to decimal and then each decimal to its equivalent hex value. On the left side, we get 8 plus 4, which equals 12. And on the right side, we get 4 plus 1, which equals 5. If we convert those to hex, 12 decimal is the equivalent of C in hex, and 5 decimal is the equivalent of 5 in hex. Therefore, 197 in decimal is C5 in hex, or it can also be written with a 0x preceding it to indicate that what follows is written in hexadecimal. Lastly, let's look at converting from hex to decimal, but this time we'll convert to binary first instead of going straight to decimal like I did in the first example. I'll convert the hex 9F to decimal. First, convert each hex symbol to its 4-bit binary equivalent. I have hex 9, which is the same as decimal 9, and that gives me 1001. And then I have hex F, which is equivalent to decimal 15, and that gives me 1111 in binary. Next, I'll combine them into one 8-bit binary number. So here I have the first 8 place values in binary, and then I'll convert to decimal, and that gives me 128 plus 16 plus 8 plus 4 plus 2 plus 1, or 159 in decimal. There are often several ways to approach converting between number systems. You should use the one that works best for you.
Mhm. Oh, yep. All right, great. She did such a great job explaining it. I encourage you to go through the content in NetAcad and make sure that you understand how to do this. You won't be able to bring any kind of calculator, I should say, calculator to the CCNA exam. If you're out in the field and you already have your job, you can just take out a calculator and you can convert hex to decimal and binary really fast. But in the exam, you're not allowed to bring any kind of calculator. So all you will have is a erase board, a small 11 by 14 probably. That's what we used in our testing center. And then you can write on it with an erasable marker. And you could draw out those tables to help you to make your conversions, but you can't just plug it into a computer. All right, so that is the end of today's presentation. And I want to encourage you to ask questions if you have them, whether you ask them in the help discussion forum or in the comments on YouTube, or in just a moment when you can ask me. I do appreciate if you rate, thumbs up my videos and follow me, and you'll be able to see future videos as well. And it's been a pleasure being your instructor for today's presentation. I'm Don Lafond, Professor Don. Oh, let me turn that off. I'm going to stop sharing so you can see me to finish. It's been my pleasure today. If you have any questions, please ask. If not, we'll see you next week in Module 6. Or if you're watching online, I guess you could just stop right now, couldn't you? Watch that one right now. All right, great. Thank you, and we'll see you again soon.